Hi, everybody. We've been talking about different types of chemical reaction, and this time we are going to talk about single displacement reactions. Now, they can also be called single replacement reactions. It is exactly the same thing. It's sort of the difference between calling it a Kleenex or a tissue. Depends on who's talking and what name they prefer, but it is the same kind of reaction. A single replacement reaction is a reaction in which one element replaces a similar element in a chemical compound. The generic form of a single replacement reaction is like this. It is an element plus a compound, element plus compound, and it evolves into a compound and an element. And it can either be the anion, which is the negative anion, or the positive cation that is replaced in the reaction. A more reactive element is going to replace a less reactive element. Now, to recall reactivity trends on the periodic tables, when we're talking about metals, metals get more reactive as you go down and to the left. So francium is our most reactive metal, and nonmetals get more reactive as you go up and to the right, and fluorine is our most reactive nonmetal. In this single displacement reaction, one of the things that I always hold on to in my brain is it looks very much like a couple that's dancing on the floor and somebody cuts in. So let's say Minnie Mouse here is dancing with Donald Duck, and Mickey comes along and taps Donald on the shoulder and says, "I say, old man, may I cut in and dance with Minnie Mouse?" And Donald gets ejected and Mickey takes his place. So you've got a single element, a compound of two things together, and afterwards the thing that was previously bonded is now alone. So Donald was bonded as part of a compound. He is now alone, and you have a new compound that's produced. The new compound that's produced is more chemically stable than the original compound that was there. There was a greater chemical affinity for the incoming element. Mickey Mouse has a greater affinity for Minnie than Donald has for Minnie, if we're going to put it in mice parlance, I guess. Here's a great example of a single replacement reaction. These are commonly used to remove metal in situations where you have ore and you're going to process that ore. Iron oxide or iron ore that comes from iron mines has to be processed in order to get metal that is useful to make automobiles and cars and steel support beams for structures and things like that. Well, that iron ore is a compound. It is burned with an awful lot of carbon in the form of coal. Pure coal is just pure carbon. When these two things are burned, you have a compound. You have elemental carbon, which is an element, and when they react in this single displacement reaction, carbon comes in, reacts with oxygen, and iron is kicked out. And that's a good thing because you actually want the iron. Carbon ends up bonded with oxygen as carbon dioxide that comes out of the smokestacks. The liquid iron is then processed and poured into bars and sheets and is made into your car body. Another classic single replacement reaction is the tarnishing of silver by dihydrogen sulfide. Dihydrogen sulfide gas is what tarnishes your silver. So you might have a silver teapot, you might have some earrings or a bracelet or an ornament that's silver, and dihydrogen sulfide gas is quite common. It smells like rotten eggs. It is that rotten egg smell. I'll show you in the next slide some of the sources of dihydrogen sulfide gas. And when these two things encounter each other, the silver is more reactive than the hydrogen, kicks out the hydrogen, And so silver bonds with the sulfur and the hydrogen gas off gases and escapes. Now, that silver sulfide is this tarnishy color that is not as pretty as pure silver, and that is the silver tarnish. But this is a classic single replacement reaction. Now, you might say, where the heck is all this dihydrogen sulfide gas coming from in my life? Well, it depends on where you live to some extent. Volcanoes and things, geologic hot springs produce an awful lot of this stuff. Decaying vegetation, coal mines, that sort of situation are going to produce an awful lot of it. And quite frankly, human bodies produce an awful lot of it. If you eat, or people you love eat, foods that are high in sulfur, they tend to emit gases. And I don't want to be too blunt about this, but they're going to produce stinky gases. And some of those stinky gases are dihydrogen sulfide. I had a student many years back who will forever remain nameless. He was a sweetheart of a guy, but I remember him saying he ate 6 eggs every single day for breakfast. You could tell he smelled like dihydrogen sulfide gas a lot. And so, yeah, I never had the heart to tell him that he smelled like that, but you could tell. Now, a way to clean tarnish off of your silver is to do another common, simple single displacement reaction. This is a kind of a at-home, non-toxic way to remove tarnish, and that is to line some sort of an aluminum, line a bowl with aluminum foil. You need to add some salts to provide some ions just to move the ions around, baking soda and plain old ordinary table salt really well. Cover whatever you're dealing with hot water, and then put your tarnished silver within it. Let it sit for a few minutes, and then let the bubbles begin and let the ions move. The silver sulfide, which is the tarnish, is going to have a single replacement reaction with the aluminum in the foil. The aluminum in this particular reaction is more reactive than the silver. It will come in, it will kick out that silver, and then it will take its place. So it actually is going to get rid of that tarnish off of your ornament or your earrings or your granny's teapot. The challenge whenever you polish silver, my friends, is you are removing some silver atoms. And so if you do it forever and ever, day after day, if it is silver plated, you will eventually remove the finish. So be careful of that. Another common single replacement reaction is ones that produce hydrogen gas with a metal. So if you take a metal and you add it to some sort of an acid, a metal plus an acid will commonly produce hydrogen gas and some sort of a chemical salt in solution. Element plus a compound gives you a compound plus an element. And if it's a metal and an acid, this is a real common single replacement reaction. So let's see if you got the hang of this and if we can predict the outcome. Halogens can replace other less reactive halogens in single replacement reactions. So we've got sodium bromide reacting with chlorine gas. And this is, I'm telling you, it is going to be a single replacement reaction. We have an element plus a compound, and we're going to end up on the other end with a compound plus an element. So the chlorine, which is more reactive, it is above bromine on that periodic table, more reactive. Chlorine's going to come in, and it is going to kick out bromine and take its place. Well, without doing an awful lot of bonding, you probably know that sodium and chloride produce sodium chloride. We've done a lot of this through this class, so you probably know what that's going to be. And if sodium bromide is aqueous, this is going to be salt water. And bromine, well, bromine in an elemental form is going to be Br. It's one of the dirty 7. And in its elemental form, it is a liquid. How do I know that? Because on the periodic table, It is red for a liquid, and bromine is a pretty kind of a brownish rust color. I included some pictures because this is a common chemical reaction done in a lot of lab experiments, and you end up with kind of a browny red liquid as the product, and it's an indicator that you have elemental bromine produced. Here's another really lovely, fun single replacement reaction. Silver nitrate in solution, aqueous, plus copper solid. Now that's what's going on in this beaker. The next two pictures are indicators of what's happening over time. Single replacement, we have a compound plus an element, and it's going to give us a different compound plus an element. Now, the metal here this is a metal and this is a metal. So the metal is going to replace the metal. Copper is going to come along, kick out the silver, and take its place. So let's remember some of the bonding that we've done in the past. Copper can either be a copper plus 1 or a copper plus 2. And you might go, I don't know which one we've got. I've done more chemistry than you have. And I know that if the solution is blue, if we have a blue solution, that means we have copper plus 2. So we have copper plus 2, and it's going to react with this ion, nitrate. So I have Cu plus 2, nitrate, NO3, nitrate, NO3 minus 1. So this is going to be, when we crisscross, this goes there and this goes there. Cu1, we don't write ones, NO3, 2. We can tell from the picture it's in solution, so this will be aqueous, plus the silver metal got kicked out, and you get solid silver. And this is such a fun chemical reaction because when you do it in the lab, that fluffy stuff that's accumulated, that is solid silver. What a fun thing. You start with a clear liquid and you end up with solid metallic silver as a product out the other end. All right, friends, those are single displacement reactions, and we'll look at double displacement next. See you then.